Hello, and welcome, fellow explorer of the cosmos. Before we dive deep into the mysteries of space and time, make sure to subscribe so you never miss a journey through the universe's hidden rhythms. Tonight, we drift gently into the fabric of space-time itself, tracing its subtle curves and bends. You'll observe how massive stars and black holes shape the flow of time, how light stretches across billions of years, and how every gravitational ripple carries the record of cosmic history. Let your mind settle, your thoughts slow, and your curiosity drift with the universe as we explore the real science behind the bending of space and the secrets it may hold about time travel. Relax, breathe, and allow the cosmic journey to begin. You start by letting your mind settle into the idea that space and time are not separate entities. They are intertwined, forming a continuum that stretches in all directions. This continuum, known as space-time, is the very framework that supports everything in the universe. You feel it as an invisible structure, not in the sense of a surface you can touch, but as the stage upon which all motion and events occur. Every star, planet, and particle moves along this fabric, responding to its shape and curvature. Gravity is not merely a force pulling objects toward each other. It is the result of the way mass bends space-time around it. You visualize a planet, quietly occupying its place in the cosmos. The mass of the planet gently warps the surrounding space and time. Objects nearby do not move toward it because of an unseen tether, but because they follow the natural curvature of the space-time that the planet creates. This bending is subtle and precise, measurable with sensitive instruments. You consider the first direct evidence of this bending, seen in gravitational lensing. When light from distant stars passes near a massive object, such as a galaxy or black hole, its path shifts ever so slightly. This effect has been observed in countless telescopic images. You imagine tracing the path of a photon, a particle of light, as it bends smoothly around a massive cluster of galaxies, arriving slightly offset from the straight line you would have expected. The universe quietly demonstrates that space itself can curve, guiding even light along its contours. Time itself is affected in the presence of mass. Clocks positioned closer to a massive object tick a fraction more slowly than clocks farther away. You picture atomic clocks, precise to billionths of a second, suspended at different altitudes. Measurements confirm that clocks at lower altitudes, nearer to Earth's mass, run slightly slower than clocks at higher altitudes. You sense this effect, not as a dramatic distortion, but as a gentle, measurable stretching of temporal flow. The universe teaches that time is not uniform everywhere, and you absorb this knowledge in the quiet of your thoughts. Even motion influences time. As you follow an object moving at high speeds, approaching the speed of light, you understand that time for the moving object slows relative to a stationary observer. This phenomenon, known as time dilation, is confirmed in particle accelerators where fast-moving particles live longer than their stationary counterparts. Your mind softly tracks these measurements, acknowledging that the universe is precise in its rules and that time can stretch and compress without breaking. You feel the subtle rhythm of this cosmic clockwork. You explore the mathematics behind these ideas without letting numbers dominate your focus. Einstein's equations, at their core, describe how mass and energy determine the curvature of spacetime. The equations are precise, tested repeatedly, and supported by observational data. You sense that the universe is not chaotic but exquisitely structured. Every curvature, every adjustment in time, has a reason rooted in the presence of matter and energy. You rest in the understanding that these laws operate consistently across the vast reaches of space. Observations from the motion of planets, the bending of starlight, and the behavior of satellites provide continuous confirmation. For example, the orbit of Mercury deviates slightly from what classical Newtonian predictions would suggest. When measured over decades, these deviations match exactly the predictions of general relativity. You follow the path of Mercury in your imagination, noting how its orbit subtly shifts, guided by the curvature of spacetime generated by the Sun. Even these small differences reveal the universe's deep geometry. You allow your awareness to extend outward, beyond the solar system, to distant galaxies and cosmic structures. Clusters of galaxies warp spacetime collectively, causing measurable distortions in the light that reaches Earth. Telescopes capture arcs and rings of light around these massive clusters, each image confirming that spacetime bends under the weight of cosmic matter. You feel a quiet satisfaction in knowing that this bending is not speculative, but a consistent, observable feature of the universe. The effect of gravity on time becomes even more apparent near extreme objects, like neutron stars and black holes. Atomic clocks sent near these objects experience measurable slowing of time, while clocks far away continue at their normal pace. Observations of pulsars, rapidly rotating neutron stars emitting steady radio signals, confirm these relativistic effects. You picture receiving these signals, precise and unwavering, and notice how the timing shifts slightly due to the gravitational curvature along the path. Time itself has a measurable elasticity, stretching and compressing according to the universe's design. Even in the calm of your own surroundings, you realize that you live within this flexible fabric. Earth's mass bends spacetime around you every moment, guiding the motion of everything from falling apples to orbiting satellites. The concept is vast, yet you feel it as an intimate part of your world. You perceive that understanding spacetime is not merely an academic exercise, but a way to comprehend the rhythm of existence itself. You recognize that each movement, each tick of a clock, is part of a subtle cosmic flow. Experimental evidence reinforces this understanding. Atomic clocks flown on airplanes, rockets, and satellites all demonstrate time dilation effects consistent with relativity. GPS systems, which require extreme precision, must correct for both gravitational and velocity-induced time differences. Your mind absorbs the fact that technology in daily life operates in perfect harmony with these cosmic principles. You sense the quiet certainty that the universe follows predictable, observable laws. Your imagination slowly drifts to the broader cosmic geometry. Massive structures, including galaxies, clusters, and superclusters, collectively shape the universe's large-scale spacetime curvature. Observations of cosmic microwave background radiation provide additional confirmation, revealing minute fluctuations that align with theoretical predictions. You feel a gentle sense of order in the universe, a continuous web of geometry connecting every object, every photon, and every instant of time. You notice that your perception of space and time has softened. You understand that neither is absolute, and yet both are precise in their behavior. You feel an awareness that spacetime is not only the framework in which everything exists but also an active participant in guiding the paths of matter and energy. This realization, rooted in observation and experiment, settles calmly in your mind. You begin to sense that the universe is a dynamic, flexible stage where time itself is part of the physical landscape. As your thoughts rest in this quiet understanding, your awareness begins to perceive the influence of motion and mass more deeply. The subtle stretching and bending of time around massive objects, and the gentle curvature of space that guides planets and photons alike, hint at how motion, speed, and gravity interact. The universe quietly shows that even as you observe it, the flow of time is intertwined with the shape of space itself, inviting further exploration into the delicate ways motion can shape the experience of time across the cosmos. You begin by allowing your awareness to settle on gravity, not as a mysterious force, but as the natural bending of spacetime by mass. You sense that every object with mass, from a pebble to a planet, shapes the fabric of space and time around it. The effect is subtle in everyday life, almost imperceptible, yet measurable with precise instruments. Even Earth itself, beneath your feet, stretches and curves spacetime in a continuous, predictable manner. You imagine this bending as a gentle gradient, gradually altering the flow of time nearby. Atomic clocks, suspended at different heights above Earth, reveal the quiet effect of gravity on time. Clocks closer to Earth's surface tick marginally slower than those at higher altitudes, an effect predicted by Einstein's general relativity. You follow the meticulous experiments that confirm this. Rockets carrying clocks, airplanes circling the globe, and satellites in orbit all demonstrate the same gentle discrepancy. Each observation reinforces that time is not uniform, but influenced by the curvature of spacetime around mass. You picture the Half-Keating experiment, where atomic clocks were flown around the world in commercial airplanes. The clocks experienced minuscule but measurable changes in elapsed time compared to clocks remaining stationary on the ground. You sense the precision required. Fractions of a billionth of a second mattered, yet the results aligned perfectly with theoretical predictions. This quiet dance of measurement shows the universe responding exactly as relativity describes, linking gravity directly to the pace of time. Gravity's influence is not limited to small scales. You extend your awareness to the sun, a massive star whose gravity subtly slows time in its vicinity. You follow the orbits of planets, noting that their paths are guided not by invisible strings but by the gentle bending of spacetime. Mercury, in particular, moves along a slightly altered orbit that would seem anomalous without considering the sun's gravitational curvature. Observational data collected over decades confirms these predictions, revealing the precise connection between mass, gravity, and temporal flow. Even closer to Earth, you notice the effect on everyday systems. GPS satellites orbit our planet at high speed and at altitude, and their onboard clocks must account for both the velocity-induced time dilation and the gravitational time differences. Without these corrections, navigation would drift by kilometers within a single day. You feel the quiet significance of this. The flow of time is a measurable, physical property, intimately linked with the curvature of spacetime, and our technology depends on this understanding to function accurately. You consider the scientific principle at work. Time passes at different rates depending on the strength of the gravitational field. Near massive objects, time slows relative to regions of weaker gravity. You visualize a clock descending toward a large planet or star. Each tick of the clock stretches slightly compared to a distant observer. This stretching is not noticeable in daily life, but measurable experiments reveal it consistently. Gravity, you realize, is a shaper of time as well as space. Experiments extend even to extreme gravitational environments. Astronomers observe neutron stars and white dwarfs, remnants of collapsed stars with enormous mass packed into small volumes. Surrounding clocks, whether hypothetical or inferred through pulsar timing, experience profound temporal slowing relative to distant observers. These observations, combined with general relativistic calculations, confirm that the universe behaves predictably even under conditions far beyond human experience. You absorb this understanding with calm curiosity, feeling the consistency of nature. You trace how light interacts with gravity as well. Photons traveling near massive bodies experience slight delays due to the curvature of spacetime, an effect measured through precise astronomical observations. Radar signals bounced off planets, like Venus or Mercury, take subtly longer paths than expected because of the sun's gravity. You sense the quiet elegance of these measurements. Even the speed of light, constant in local frames, interacts with the geometry of spacetime to produce measurable effects over vast distances. Gravity gently guides not only matter but the flow of light and information. The concept of gravitational time dilation reveals itself in cosmic observations. Pulsars, those rapidly spinning neutron stars, emit pulses of radio waves with extraordinary regularity. When these pulses pass near massive objects, the timing shifts slightly, confirming the curvature of spacetime and the slowing of time under gravity. Each pulse, arriving decades later at Earth-based detectors, carries a precise record of relativistic effects. You imagine listening to these distant ticks, each one a testament to the universe's predictable response to mass and energy. Even human physiology is affected subtly by these effects, though imperceptibly in daily life. Astronauts on the International Space Station experience minuscule time differences compared to people on Earth, due to both their speed and the slightly weaker gravitational field in orbit. You feel a gentle connection between your understanding of physics and the lived experience of those who navigate beyond the planet's surface. Time, you realize, is not uniform but a flexible dimension shaped by both motion and mass. You explore the mathematical foundation behind these observations without needing to focus on equations. General relativity describes how mass and energy warp spacetime, producing both the gravitational attraction we feel and the differential flow of time. Predictions from these equations have been confirmed in laboratories, in satellites, and across the cosmos. Your mind rests in the understanding that these principles are not hypothetical. They are observable, repeatable, and consistent with the universe's behavior at every scale you consider. This understanding leads naturally to imagining how different masses, from mountains to stars to black holes, create local variations in the passage of time. Even subtle differences, measured in billionths of a second, accumulate over years and decades, confirming the reliability of these predictions. You sense that spacetime is an active participant, gently modulating the rhythm of time depending on the presence and distribution of mass around it. Each experiment, each observation, reinforces this connection. Gravity's influence on time also shapes the dynamics of orbits and trajectories. Satellites, spacecraft, and planetary motion all follow paths dictated not only by the apparent pull of gravity but by the curvature of spacetime itself. Every maneuver, every orbital calculation, implicitly accounts for the slow stretching of time in gravitational wells. You feel the precision of this cosmic choreography, where physics and observation align seamlessly. Time and gravity are inseparable aspects of the same structure. You reflect on the quiet power of this knowledge. Understanding how gravity slows time changes the way you perceive motion and rest, near and far, slow and fast. The universe operates according to rules that are measurable, predictable, and deeply consistent. Even as you rest in your calm awareness, you feel the subtle flow of time as a variable property, intimately linked to the mass and energy surrounding you. Your mind settles into the rhythm of this cosmic order. As your awareness drifts outward, you sense the broader implications. Time is shaped not only by local gravity but by the motions and masses throughout the universe. The gentle slowing of clocks near massive bodies foreshadows the more extreme effects near objects like black holes. The universe, you realize, offers a continuum of temporal experiences, from the everyday flow on Earth to the stretched, deliberate passage of time in the presence of immense mass, quietly revealing the connection between gravity and the movement of every moment. You begin by noticing that light travels at a remarkable, unchanging speed, an exact value measured across countless experiments. Every photon moves at this constant pace through the vacuum, forming a fundamental standard that links space and time. You imagine sending a beam of light across the quiet emptiness between planets and stars, observing that its journey remains steady and unwavering, unaffected by most motions you can perceive. This constancy underlies much of modern physics and provides a natural ruler for measuring the universe. Light carries not only distance but also time. When you observe light from a distant star, you are witnessing events that occurred long ago, sometimes millions or even billions of years in the past. Your awareness traces the journey of these photons, emitted, perhaps, before your own planet formed. The constancy of their speed allows you to calculate their distance and the timing of cosmic events with precision. Each arrival of light at your instruments or eyes encodes information about the space it traversed and the curvature it experienced. Gravity subtly alters this journey. As a photon passes near a massive object, its path bends ever so slightly. This phenomenon, known as gravitational lensing, has been observed in images captured by telescopes across the world and in space. You imagine a beam skimming past a galaxy cluster, curving imperceptibly under the influence of the cluster's mass. Observers far away record this deflection and, using precise calculations, confirm the predictions made by Einstein's theory of general relativity. Light acts as a natural probe of the universe's geometry. Even small masses influence light. Experiments during solar eclipses in the early 20th century measured starlight passing near the sun, demonstrating that the apparent positions of stars shift subtly due to the sun's gravity. Your mind gently follows these shifts, appreciating the delicate measurements required and the precision of the resulting confirmations. Light, though intangible, reveals the contours of space-time, offering insight into the invisible structure shaped by mass and energy throughout the cosmos. You consider the relationship between light, time, and space. Because light travels at a fixed speed, the passage of time and the measurement of distances are intimately connected. Moving observers experience time differently, yet the speed of light remains constant for all, forming the foundation for understanding relativistic effects. Your mind observes that this constancy sets limits on how information and energy propagate, shaping the very structure of causality and sequence in the universe. The redshift of distant galaxies provides another way light functions as a cosmic ruler. As the universe expands, the wavelength of light stretches, shifting toward the red end of the spectrum. You imagine observing a distant galaxy, its light traveling for billions of years, gradually stretched by the expansion of space itself. Measuring this redshift allows astronomers to calculate distances and map the large-scale structure of the universe, providing direct evidence of cosmic expansion. Light becomes a messenger carrying both distance and the history of spacetime. Light also enables the measurement of incredibly small distances and intervals of time. Laboratory experiments, including interferometry and atomic clocks synchronized by lasers, rely on light stability. You feel the precision inherent in these methods, noting that even minute deviations in light travel can be detected and used to refine measurements of fundamental constants. The behavior of light underpins our most accurate assessments of time and space, providing a foundation for both terrestrial technology and astronomical observation. You follow light into more extreme environments. Near neutron stars or black holes, photons experience significant curvature due to the intense warping of spacetime. Observations of X-ray emissions, gravitational lensing, and orbital motion of nearby stars all confirm that light's path bends in measurable ways under strong gravity. Your mind visualizes these deflections, slow and precise, emphasizing that even under extreme conditions, the universe behaves predictably. Light acts as both a probe and a guide to the universe's underlying structure. The arrival of light also conveys information about motion. Doppler shifts, detected in starlight, indicate whether objects are moving toward or away from you. Observing these shifts, you can trace the velocities of distant stars and galaxies, and even detect the motion of planets around other stars. Your awareness of light as a dynamic signal emphasizes its dual role, both a ruler of space and a messenger of motion. Every photon carries an exact record of its journey, revealing both distance and speed in precise, measurable terms. Pulsars, the rapidly spinning remnants of massive stars, emit beams of light and radio waves with remarkable regularity. You sense the precision of these cosmic clocks, observing how slight variations in arrival times reflect gravitational effects or motion through spacetime. Light provides not only distance and position but also a clock for measuring the passage of time across the universe. This precision allows astronomers to test theories of relativity with extraordinary accuracy, confirming the predicted effects of both motion and gravity on temporal flow. Light's interaction with matter is equally revealing. Spectroscopy measures the absorption and emission of light by atoms and molecules, providing detailed knowledge about composition, temperature, density, and motion. You follow photons emitted from distant nebulae, tracing the fingerprints of chemical elements across space. These measurements confirm that the same physical laws operate universally, from local laboratories to the most distant galaxies. Light becomes a precise tool for mapping the properties of the universe, revealing structure and dynamics across vast scales. You reflect on the combination of light and gravitational curvature. Observing lensed quasars, supernovae, or clusters of galaxies, you see how light's path is stretched and bent, allowing distant objects to appear multiple times in the sky. You recognize that this is not an illusion, but a direct observation of spacetime's geometry. Light, constant in speed yet influenced by curvature, encodes information about both distance and the mass that shapes its path. Your mind absorbs the interplay of light and gravity as a consistent and measurable feature of the cosmos. Even in everyday life, light serves as a precise reference. Laser ranging experiments measure the distance to the moon with centimeter accuracy, relying on the predictable speed of light. Optical clocks synchronized with laser pulses provide the most accurate measurement of time ever achieved, sensitive to variations caused by altitude differences or gravitational shifts. You notice that the same principles governing the cosmos also govern these experiments on Earth, reinforcing the universality of light as a standard for space and time. Your awareness gradually expands to the large-scale universe. Light from billions of galaxies traces the cosmic web, revealing clusters, voids, and filaments. By measuring the paths and distortions of these photons, astronomers map the universe with exquisite precision. Each observation relies on the constancy of light speed and its interaction with spacetime, confirming the predictions of general relativity across immense scales. Light acts as both a ruler and a record, enabling you to follow the shape and history of the cosmos itself. As your mind rests in this understanding, you feel the connection between the flow of time and the structure of space revealed by light. Its unwavering speed, its interaction with mass, and its capacity to carry both distance and history create a foundation for all cosmic measurement. You sense that the universe is structured in a way that allows information to travel consistently, and that the bending of light by gravity opens a window into the very curvature of space and time, inviting further reflection on the subtle ways motion shapes the experience of time itself. You begin by letting your mind settle on the idea that motion affects the passage of time. Imagine two identical clocks, perfectly synchronized. One remains still, while the other moves at a speed approaching that of light. According to Einstein's special theory of relativity, the moving clock ticks more slowly relative to the stationary one. This is not an illusion or a matter of perception. It is a measurable, physical effect, verified through precise experimentation and observation. Time itself is influenced by velocity. You picture the moving clock carried aboard a spacecraft, gently tracing a path through the cosmos. Even at speeds much slower than light, the effect is present, though extremely small. Your mind focuses on the subtle differences, realizing that with highly precise instruments, these discrepancies can be observed and measured. The universe operates consistently, ensuring that clocks, whether stationary or moving rapidly, follow the rules of relativity. Time adapts to motion with quiet precision. The concept of time dilation is observed in particle physics. Particles called muons, created in the upper atmosphere by cosmic rays, decay in a predictable span when at rest. Yet when moving at high velocity toward the Earth's surface, they survive longer than expected. You sense the clarity of this evidence. The faster an object moves, the slower its internal processes occur relative to a stationary observer. The cosmos demonstrates the malleability of temporal experience under motion. You imagine astronauts aboard a high-speed vehicle circling the Earth. Their clocks, though only slightly different from those on the planet's surface, reveal the same principle. Even tiny variations, measured in billionths of a second, are consistent with theoretical predictions. Your awareness stretches to consider that every particle, every system experiences this effect. The passage of time is not absolute but depends on velocity in a measurable, predictable way. You rest in the certainty of this knowledge. You focus on the mathematics without being overwhelmed. The Lorentz factor, derived from the equations of special relativity, defines precisely how much slower time passes for a moving object. You feel the calm order of this relationship. As speed approaches the speed of light, time slows more dramatically. This is not speculation. It is confirmed repeatedly in experiments involving subatomic particles, atomic clocks, and fast-moving spacecraft. Your mind absorbs the precision inherent in these measurements. You consider the thought experiment of twins. One stays on Earth, the other travels on a spacecraft at near light speed. When the traveler returns, they are younger than the twin who remained behind. This is not merely a mental exercise. It is a direct consequence of time dilation. Your awareness drifts through the scenario, observing the traveler's internal clock and the earthbound twin's clock. Each moment for the moving twin stretches slightly compared to the stationary twin, resulting in a measurable age difference over the journey. Particle accelerators provide further confirmation. Particles accelerated close to the speed of light demonstrate extended lifetimes, consistent with relativistic predictions. Muons and other unstable particles exhibit delayed decay precisely as calculations indicate. You feel the subtle beauty of this consistency. The universe does not bend rules arbitrarily. Instead, motion interacts with time in a predictable, precise manner. Each observation reinforces the reality that time is not a fixed quantity but a dimension responsive to speed. GPS technology offers a tangible, everyday demonstration. Satellites orbiting Earth move at high velocities and experience both velocity-induced time dilation and gravitational time dilation. Their onboard clocks tick differently than clocks on Earth's surface, necessitating precise adjustments to maintain accuracy. You imagine the continuous corrections, the delicate synchronization required to ensure that signals reach devices correctly. Here, the principles of relativity are not abstract. They are integral to modern life, quietly governing systems you rely on every day. You explore how motion and acceleration interact. While special relativity primarily addresses constant velocities, accelerated frames, such as those experienced by a spacecraft turning or slowing, require additional consideration. General relativity explains how acceleration is equivalent to gravity in its effect on time. You sense the smooth continuity of these principles, understanding that both velocity and gravitational influences shape temporal flow. The universe offers a coherent framework connecting motion, mass, and time itself. You imagine following a photon, a particle of light, as it traverses space at its constant speed. From its perspective, time does not pass. It moves instantaneously from emission to absorption. Although this perspective is abstract, it reinforces the idea that the passage of time is linked to the observer's motion. You rest in the realization that each frame of reference, each velocity, provides a distinct, measurable experience of temporal flow. Time is flexible yet consistent, adapting to motion and mass alike. You reflect on the implications for understanding your own experience. Motion affects not only particles and clocks but also all processes, including biological ones, albeit at imperceptibly small scales under normal conditions. Astronauts on long-duration missions experience minuscule temporal shifts compared to those on Earth, demonstrating that even life itself is subtly bound to the rules of relativity. You feel the quiet certainty that the universe's laws operate consistently, at every scale and in every frame of reference. Observations of rapidly moving astronomical objects, such as stars orbiting near black holes, provide natural laboratories for time dilation. Pulsars moving at high velocities emit pulses that arrive with slight delays due to relativistic effects. By tracking these variations, astronomers confirm predictions about time flow at extreme speeds. You sense the meticulous precision required to detect these differences and the calm reliability of the underlying physics. Time responds to motion predictably, regardless of scale or distance. You explore the interplay of velocity and gravitational fields. A moving clock in orbit experiences both the slowing effect of velocity and the slightly faster ticking due to weaker gravity compared to the Earth's surface. These effects can partially cancel or combine, depending on circumstances. You imagine balancing these influences, noting the precision with which scientists calculate them for satellites and deep space missions. The universe operates as a harmonious system, where time responds consistently to both speed and gravity. You consider how the twin paradox might extend to interstellar travel. A spacecraft approaching light speed could traverse vast distances, while the traveler's personal time would pass far more slowly than that of observers on Earth. You sense the quiet reality that this is not science fiction, but a natural consequence of relativity. Though current technology cannot achieve such speeds, the principles remain experimentally verified. Your mind rests in the knowledge that time is responsive, precise, and consistent across all frames of motion. Even in subtle, everyday motions, the effect persists, though imperceptible. The passage of time varies slightly between objects moving relative to each other, yet the difference is so small that it requires atomic precision to detect. You imagine measuring these differences, one tick at a time, appreciating the universality of the effect. Time, in all its flexibility, maintains perfect consistency within the rules defined by the universe, offering a precise framework for both motion and observation. As your awareness settles, you feel the full scope of motion's impact on time. Each velocity, each journey through space, subtly stretches or compresses personal temporal experience. The universe confirms this with unerring precision, from particle accelerators to orbiting satellites to pulsars across the galaxy. You sense that the flow of time is intimately tied to motion, gently reminding you that even the simplest acts of moving through space carry consequences in the rhythm of existence. This understanding naturally opens awareness to how extreme gravitational environments might shape time even further. You allow your awareness to settle on the concept of a black hole, a region of space where gravity becomes so intense that nothing, not even light, can escape. You picture a star that has exhausted its nuclear fuel, collapsing under its own weight until it becomes an incredibly dense point. Surrounding this point is a boundary known as the event horizon. Beyond it, the gravitational pull is so strong that escape is impossible. You sense the quiet power of this region, not as a threat, but as an extreme example of how spacetime responds to mass and energy. Time near a black hole behaves in a manner profoundly different from your everyday experience. Clocks positioned near the event horizon tick more slowly relative to distant observers. You imagine a clock hovering near this boundary, its hands moving at a deliberate, stretched pace. From far away, you would see each tick drawn out, as if the flow of time itself were slowing under the immense curvature of spacetime. This effect is a direct consequence of general relativity, verified repeatedly in extreme astrophysical environments. The evidence for these predictions comes from a variety of observations. X-ray emissions from matter falling into black holes, known as accretion disks, display specific patterns consistent with relativistic time dilation. Material spirals inward, heated to extraordinary temperatures, and emits light in frequencies that astronomers can detect and measure. You follow these photons across vast distances, noting how their timing and energy reveal the extreme gravitational environment from which they originated. Observations align precisely with theoretical predictions. Gravitational waves provide additional confirmation. When two black holes collide, they generate ripples in spacetime that propagate outward at the speed of light. These waves, detected by instruments such as LIGO and Virgo, carry information about the masses, velocities, and interactions of the colliding black holes. You feel the subtle certainty of this evidence, as these measurements confirm the warping of spacetime and the time dilation effects predicted by relativity. The universe communicates its structure in these gentle ripples. You consider the path of a spacecraft approaching a black hole. As it draws closer to the event horizon, time for those aboard would pass more slowly relative to observers far away. Even if the spacecraft remained intact, the flow of time inside would diverge from that outside. You visualize this divergence, a precise and measurable consequence of the curvature of spacetime. It is not an abstract idea but a directly observable effect confirmed through both calculations and astrophysical evidence. The Schwarzschild radius defines the size of the event horizon for non-rotating black holes. You imagine measuring this radius proportional to the mass of the black hole. For a black hole with several times the mass of the Sun, the event horizon spans kilometers. Yet within this boundary, space and time are intricately and profoundly curved. Matter and energy within this radius follow paths dictated entirely by the geometry of spacetime. The universe demonstrates an extreme, yet predictable relationship between mass, gravity, and time. You explore the behavior of matter outside the event horizon. Stars orbiting close to supermassive black holes, such as the one at the center of our galaxy, move along paths determined by the intense curvature of spacetime. Their speeds and trajectories provide precise measurements of the black hole's mass and influence. Observations of these orbits, confirmed over decades, offer one of the most direct pieces of evidence for the existence of black holes and the effects of extreme gravity on time. You follow the stars' movements with calm attention. Time dilation near black holes also affects light. Photons emitted from matter near the event horizon take longer to reach distant observers. Their frequencies shift toward the red, a phenomenon known as gravitational redshift. You imagine measuring this shift with a telescope, noticing the precise way in which the extreme gravity stretches both the light's wavelength and the apparent passage of time. Each photon carries an exact record of the curvature it traversed, providing a natural, observable clock for the processes occurring near the black hole. Rotating black holes or Kerr black holes introduce additional complexity. The rotation drags spacetime around with it, a phenomenon known as frame dragging. You visualize this rotation gently twisting the paths of nearby objects and light. Observations of stars and gas clouds orbiting these black holes confirm the predicted twisting of spacetime. You sense the precision with which astronomers measure these effects, tracking subtle deviations and confirming that the universe behaves according to the exact rules outlined in general relativity. You consider the immense tidal forces near a black hole. Matter falling toward the singularity experiences extreme stretching and compression due to the gradient of gravity. This effect, known as spaghettification, occurs when the difference in gravitational pull between different parts of an object becomes extreme. You note that these forces are not arbitrary but calculable, predictable consequences of the gravitational curvature. The universe operates with remarkable precision, even in these most extreme conditions. Black holes also influence their surroundings on a larger scale. Their gravity can direct the motion of gas clouds, trigger star formation, and affect entire galactic dynamics. Observations of quasars, powered by matter accreting onto supermassive black holes, show immense energy release that astronomers can measure across millions of light-years. Each signal reflects the underlying geometry of spacetime and the flow of time in the black hole's vicinity. You sense that even at vast distances, black holes shape the behavior of matter and light in measurable, precise ways. Your awareness gently extends to hypothetical observers near a black hole. If a person could safely hover at a stable point just outside the event horizon, they would experience time at a much slower rate than someone far away. Even small intervals for the distant observer could correspond to much longer durations for the nearby observer. You imagine the quiet regularity of these intervals, measurable in principle, illustrating that time is intimately linked to gravity. The universe offers a coherent framework where extreme curvature modulates the pace of temporal experience. You reflect on the consistency of observations across multiple black holes. Stellar mass black holes and supermassive black holes both exhibit the same fundamental effects. Time slows near intense gravity, light curves, and orbits follow the contours of spacetime. You perceive the universality of these principles, demonstrating that the rules of relativity hold at every scale. Observational evidence, ranging from X-rays to gravitational waves to stellar orbits, confirms that these predictions are not abstract but precise features of reality. Even the most extreme gravitational environments provide a predictable laboratory for understanding time. The event horizon serves as a natural boundary where the curvature of spacetime becomes profound. Material outside this boundary emits light and energy that can be measured, allowing precise confirmation of relativistic effects. You sense the quiet reliability of the universe, where time, space, and gravity interact according to exact, measurable laws. Every observation aligns with the predictions of general relativity, reinforcing the coherence of cosmic mechanics. As your awareness rests in this understanding, you notice that time is not uniform across the cosmos. The passage of each moment depends on the surrounding mass and the strength of gravity. Near a black hole, time stretches and slows, creating an extreme illustration of principles you have already encountered in gentler forms on Earth and in orbit. The universe demonstrates, with quiet precision, that time is flexible, responsive to the distribution of mass, and shaped by the curvature of space. You feel the subtle invitation to consider how hypothetical bridges in spacetime might connect distant regions, guided by this same curvature. You begin by considering spacetime as a flexible fabric that can be warped and bent in extreme ways. If massive objects curve space and slow time, you wonder what would happen if the curvature became so intense that distant regions could connect. Solutions to Einstein's equations suggest the possibility of such structures, known as wormholes. These are not fantastical portals, but mathematical predictions based on general relativity, describing tunnels through the geometry of spacetime itself. A wormhole can be envisioned as a passage linking two separate points in spacetime. You imagine a tube not made of matter in the conventional sense, but a region where the fabric of space is shaped differently, allowing travel between locations that would otherwise be far apart. The mathematics shows that if a stable wormhole could exist, it would provide a continuous path through the universe, a feature governed entirely by the curvature of spacetime rather than any conventional propulsion. The simplest type of wormhole solution, known as the Einstein-Rosen bridge, arises from the equations describing black holes. It links two separate regions, but in its natural form, it is unstable and collapses quickly. You picture the fleeting structure, collapsing before anything could traverse it, emphasizing that these solutions are not yet practical or observed directly. Yet, the equations demonstrate that the universe allows for configurations of spacetime far beyond what is seen in everyday life. For a wormhole to remain open and stable, theoretical models require unusual forms of matter, sometimes called exotic matter, with negative energy density. You imagine this matter gently counteracting the natural tendency of the tunnel to collapse. While this matter has not been observed in laboratory conditions, quantum field theory predicts circumstances under which negative energy densities could exist, at least on microscopic scales. The universe, in theory, provides the conditions to sustain extreme geometries. Observational evidence of wormholes remains indirect. Astronomers search for phenomena such as unusual gravitational lensing or shifts in light that cannot be explained by conventional mass distributions. You imagine detecting the subtle curvature of spacetime, noticing slight deviations in the paths of photons, as if they passed through an unseen, transient tunnel. Although no confirmed wormholes have been observed, these investigations rely on the same precise principles of measurement and prediction that confirm black holes and gravitational waves. Wormholes demonstrate the flexibility of spacetime. While ordinary mass bends space gently, a wormhole requires curvature on a more dramatic scale. You imagine space stretching and connecting distant points, not instantaneously, but along a continuous, mathematically consistent pathway. These solutions reinforce your understanding that space and time are intimately linked, responsive to mass, energy, and the underlying equations of relativity, even in configurations far beyond human experience. Theoretical physicists explore traversable wormholes by combining general relativity with quantum mechanics. You visualize the equations guiding this exploration, revealing how energy, pressure, and curvature interact. The solutions suggest that if certain conditions were met, a traveler could, in principle, pass through a wormhole, experiencing time and space along a continuous path. Each prediction is grounded in mathematics and physical laws, emphasizing the consistency of the universe, even in extreme or hypothetical configurations. You reflect on the broader implications for time. A wormhole connecting distant regions could also link different moments in time, due to the relative passage of time along each path. While practical construction is beyond current technology, the equations indicate that time is malleable, shaped by the geometry of space and energy. You sense the profound relationship between motion, gravity, and the potential for exotic structures, noting that extreme curvature can influence both distance and duration simultaneously. Gravitational lensing provides an analog for understanding how light might behave near a wormhole. Light passing near a massive object bends along curved paths. Similarly, a wormhole would bend light in extreme ways, potentially producing observable anomalies. You imagine photons tracing unexpected arcs across the sky, revealing hidden structures in spacetime. Even if wormholes remain theoretical, studying these effects deepens your understanding of the universe's geometry and the influence of mass and energy on the flow of light and time. Quantum considerations introduce additional constraints. Wormholes interact with the vacuum fluctuations of space, and these effects may limit stability. You picture the vacuum, normally quiet and empty, generating fleeting energy fluctuations that influence extreme curvature. These interactions are not random. They follow the rules of quantum field theory and general relativity. Your mind absorbs the subtle interplay of forces, recognizing that spacetime, while flexible, remains governed by consistent, predictable laws. Even in thought experiments, traversable wormholes require careful balance. Too little negative energy, and the structure collapses. Too much, and it becomes unstable. You imagine fine-tuning this balance, guided by precise mathematical relationships, and note that the universe allows solutions that are internally consistent. While practical realization may never occur, these scenarios illuminate the potential for spacetime to adopt configurations far beyond ordinary experience, reinforcing the universality of physical laws. You explore how wormholes connect to the larger cosmic framework. Linking distant regions could, in principle, reduce effective distances, demonstrating that the universe's geometry is not strictly linear. Even without traveling, photons and gravitational influences follow paths dictated by spacetime curvature. You sense the quiet coherence of the cosmos, where geometry, motion, and energy interact to produce a consistent, measurable structure, whether or not humans ever traverse it directly. The concept of exotic matter highlights the limits of current understanding. While general relativity allows for certain geometries, the physical realization depends on energy distributions that are rare or theoretical. You consider Casimir effects, negative energy densities in quantum experiments, as a faint hint that extreme geometries might be physically meaningful. The universe you perceive contains both the rules and the possibilities, even if some remain beyond direct observation or practical construction. You reflect on the interplay between wormholes and black holes. Both involve extreme curvature, but one forms a singularity with an inescapable horizon, while the other, in theory, could provide a continuous, traversable pathway. The distinction is subtle yet profound. Both illustrate how mass and energy shape the geometry of spacetime, and both offer windows into the behavior of time under extreme conditions. Observational evidence of black holes reassures you that the predictions of general relativity remain consistent, even when extended to more hypothetical structures. Your awareness expands to consider the cosmic implications. If wormholes exist, even rarely or transiently, they could influence the distribution of matter and energy across vast scales. Light, gravitational waves, and high-energy particles could take alternate paths, revealing the hidden curvature of spacetime. You sense that these possibilities, while theoretical, provide a framework for understanding the universe's geometry, and for imagining how extreme curvature could link distant points in measurable ways. As your mind settles into these ideas, you notice the continuity of principles. Gravity curves space, mass shapes time, and the extreme solutions of Einstein's equations suggest pathways beyond ordinary distances. Wormholes remain theoretical, but they demonstrate the flexibility and precision of the universe's underlying geometry. You feel the quiet coherence of these structures and their connection to the bending of spacetime, hinting at how even the most extreme curvature can provide insight into the flow of time and the paths of motion across the cosmos. You let your mind expand, moving outward from stars and galaxies to the universe as a whole. Space is not static. It stretches and grows, carrying galaxies with it. Observations by Edwin Hubble in the 1920s confirmed this expansion, revealing that distant galaxies appear to recede from us in all directions. The light reaching you from these galaxies shifts toward longer wavelengths, a redshift, indicating that space itself is stretching over time. Each photon becomes a record of this gradual growth, carrying information about distances measured across billions of years. You focus on the cosmological principle, the observation that, on large scales, the universe appears uniform and isotropic. No location or direction is fundamentally special, which allows astronomers to model the expansion consistently. You imagine a three-dimensional grid stretching gently, with each galaxy embedded within it. As space expands, distances between objects increase, not because galaxies move through space, but because the space between them itself grows. This distinction is subtle yet profoundly important for understanding cosmic time. Redshift provides a natural measure of distance and time across the cosmos. Light emitted by a galaxy billions of years ago reaches you stretched, indicating how much the universe has expanded since that light began its journey. You sense the quiet reliability of this method. Each observation encodes both the distance traveled and the epoch from which the light originated. Astronomers can reconstruct the history of the universe, tracking how cosmic structures evolved as space itself stretched. Hubble's law quantifies this relationship. The further a galaxy is, the faster it appears to recede. You imagine plotting distances against velocities, noting the linear pattern that emerges. This pattern is not arbitrary but a direct consequence of the uniform expansion of spacetime. Your awareness rests in the precise predictability of this phenomenon, confirmed by observations across countless galaxies. The universe demonstrates both regularity and a subtle passage of time that extends beyond local effects. You consider how expansion affects the perception of time. Observers in distant galaxies experience time relative to their local environment. Yet the stretching of space influences the intervals over which light and signals travel. A supernova exploding billions of light-years away appears to you in slow motion due to both redshift and the time dilation inherent in the expanding universe. You notice that cosmic expansion is not merely a change in distance, but also a factor in the temporal experience of events across space. The cosmic microwave background provides another window into this temporal expansion. This relic radiation, emitted approximately 380,000 years after the Big Bang, carries a uniform glow across the sky. Its temperature fluctuations and redshift reveal both the age of the universe and the expansion rate. You trace these photons backward in time, observing the universe in its infancy. Their journey reinforces the notion that light is a messenger of cosmic history, stretching as space grows, and offering precise measurements of the universe's temporal structure. You reflect on large-scale structures, galaxy clusters, filaments, and voids. Their formation is guided by gravity, yet their separation increases as space expands. You notice that while local systems, such as galaxies bound by gravity, resist this expansion, the vast distances between clusters continue to grow. The universe provides a framework in which time and distance are interwoven, influenced by both the geometry of space and the dynamics of matter and energy. Each observation confirms the predictable consistency of these processes. You consider how astronomers correct for cosmic expansion when measuring events. Light from distant galaxies arrives stretched, and the apparent duration of observed phenomena is extended. A supernova, for instance, appears to unfold more slowly than it would nearby. These corrections are essential for reconstructing the true timing of cosmic events. You sense the careful precision required, appreciating how scientists use the known expansion rate to interpret observations accurately, maintaining fidelity to both distance and temporal intervals. Dark energy provides an additional layer to your awareness. Observations of distant supernovae suggest that the expansion of the universe is accelerating. You imagine a gentle, uniform force acting on space itself, subtly increasing the rate at which distances grow. This acceleration affects the way light from distant objects reaches you, slightly altering the intervals you observe. While the underlying cause of dark energy remains a subject of research, its effects are measured and incorporated into models of cosmic time, ensuring a consistent framework for understanding temporal flow across vast scales. You explore how the universe's age is determined. By combining redshift measurements, the Hubble constant, and observations of the cosmic microwave background, scientists calculate the time elapsed since the Big Bang. You visualize this timescale, spanning 13.8 billion years, and sense how cosmic expansion provides a clock that is simultaneously vast and precise. Each galaxy, photon, and cluster participates in this temporal unfolding, offering a record of the universe's growth over unimaginable distances. The expansion of space also influences the observable horizon. Beyond a certain distance, galaxies recede faster than light relative to you due to the stretching of space, limiting the region you can see. You imagine the edges of this cosmic horizon, where light emitted today will never reach you. This boundary is not a wall, but a limit imposed by the interplay of space, expansion, and time. Observations within the horizon provide a reliable window into the past, allowing measurement of both spatial and temporal structures. You consider the passage of time in a universe governed by expansion. Local clocks remain unaffected by the stretching of distant space, yet light and signals traveling across expanding distances experience delays and redshifts that encode the universe's growth. Your awareness settles on the interplay between local and cosmic scales, noticing that time is both universal and relative, shaped by distance, motion, and the stretching of space itself. Cosmic expansion subtly intertwines distance and duration. The universe's expansion also interacts with gravity. While clusters of galaxies remain bound, the space between them stretches, gently modifying the paths of light and the timing of events. You imagine a photon traversing billions of light years, its journey influenced by both curvature and expansion. Each measurement reveals the history of spacetime on a grand scale. The expansion provides a natural clock, stretching intervals and guiding your understanding of temporal flow across the cosmos. You reflect on the consistency of these observations. Redshift measurements, cosmic microwave background data, and galaxy distributions all converge to confirm the predictable expansion of spacetime. You sense the coherence of the universe, where motion, distance, and time are linked by fundamental laws. Each measurement reinforces the gentle rhythm of cosmic time, allowing you to follow the universe's growth without abrupt transitions or uncertainty. As your mind rests in this awareness, you sense that time is not uniform across the cosmos. Expansion stretches not only distances but also the intervals over which light travels, subtly modulating the passage of events. Observations of galaxies, supernovae, and background radiation reveal a precise, measurable history encoded in the universe itself. You feel the quiet continuity of cosmic time, extending awareness beyond local motions to the grand scale of the expanding universe, hinting at the interplay of energy, mass, and curvature that governs temporal flow throughout space. You begin by letting your mind settle on the relationship between mass and energy. Einstein's equation, E=mc², expresses a profound principle. Mass is a concentrated form of energy, and energy has mass-like effects on the universe. This connection is not abstract. It has measurable consequences. In particle accelerators, matter can be converted to energy and vice versa, demonstrating the precise interchangeability of these quantities. Each transformation follows predictable physical laws, offering evidence of the fundamental equivalence. You consider how energy, like mass, influences the curvature of spacetime. In general relativity, it is not just matter that shapes the geometry around it, but the entire energy-momentum content, including radiation and kinetic energy. You imagine a star radiating light across space. The photons carry energy, and even though massless, they contribute to the overall curvature, subtly affecting the paths of nearby particles and light. The universe responds precisely to energy in all its forms. Particle physics experiments provide concrete examples. In colliders, subatomic particles are accelerated to nearly the speed of light and then smashed together. The resulting energy produces new particles, sometimes with masses greater than the originals. You picture detectors capturing each collision, measuring trajectories and energies with exacting precision. These experiments confirm that energy and mass are interchangeable and that both influence the local curvature of spacetime, consistent with Einstein's equations. You focus on the life cycles of stars. Massive stars fuse lighter elements into heavier ones, releasing energy in the process. This energy sustains their structure and radiates outward as light and heat. When the fuel runs out, the star may collapse, forming a neutron star or black hole. The energy released during collapse alters the surrounding spacetime, influencing nearby matter and light. Each stage of a star's evolution provides direct evidence of the intimate connection between energy, mass, and the curvature of spacetime. Neutron stars offer extreme examples. Composed almost entirely of densely packed neutrons, their mass is comparable to the Sun, yet compressed into a sphere just a few kilometers in diameter. You sense the incredible density and the resulting gravitational field. Time near the surface of a neutron star passes more slowly relative to distant observers. Observations of pulsars, spinning neutron stars emitting periodic signals, confirm this time dilation. Energy and mass together dictate how spacetime bends, and pulsars provide precise, measurable clocks that reveal the effect. You trace the effect of collisions between black holes. When two massive black holes merge, they release tremendous amounts of energy as gravitational waves. These ripples propagate through space, carrying information about the masses and velocities of the black holes. You imagine detectors like LIGO and Virgo measuring minute distortions in spacetime, providing direct evidence of the mass-energy relationship. Each wave confirms that energy, whether in matter or motion, produces predictable curvature in the surrounding spacetime. The Sun provides a familiar example. Its mass-energy curves space, keeping the planets in orbit. The bending of light from distant stars observed during solar eclipses confirms this curvature. You picture the Earth's clock and the Sun's gravitational influence, noting that time on Earth is slightly faster than it would be closer to the solar surface. Even in this everyday context, the interplay of mass, energy, and time is subtle but measurable, demonstrating that the universe consistently applies these principles at all scales. High-energy astrophysical phenomena also reveal these effects. Supernovae release enormous energy in a fraction of a second, reshaping surrounding spacetime and triggering shock waves in the interstellar medium. You imagine photons and neutrinos racing across space, carrying both energy and information about the explosion. The mass energy released influences the motion of nearby matter and the curvature of spacetime, illustrating the tangible connection between energetic events and temporal flow across the cosmos. You reflect on relativistic particles. Objects moving at speeds approaching light carry energy that contributes to spacetime curvature. In cosmic rays, protons traveling near light speed generate measurable effects in detectors on Earth. You sense the precise relationship between energy, velocity, and curvature. Even without traditional mass, energetic motion produces measurable consequences, confirming that the universe treats mass and energy as equivalent in shaping spacetime. You explore the role of energy in cosmology. The total energy content of the universe, including dark matter, ordinary matter, and radiation, determines the overall geometry of spacetime. Observations of cosmic microwave background fluctuations and large-scale structure map this distribution. You imagine these measurements revealing how energy density affects the expansion and curvature of space, providing a cosmic scale demonstration of the equivalence of energy and mass in influencing temporal and spatial relationships. Momentum, too, contributes to spacetime geometry. Moving objects carry momentum, and this directional energy alters the curvature around them. You imagine a galaxy cluster in motion, its momentum contributing subtly to the gravitational landscape. Observations of lensing and galaxy motions confirm that both mass and momentum are accounted for in predicting the curvature of spacetime. Your mind rests in the precision of these calculations, noting the universe's consistent response to energy in motion. You consider how energy conditions constrain spacetime structures. Solutions to Einstein's equations often require that energy density be positive and behave predictably. These conditions prevent exotic, unphysical scenarios from arising spontaneously. You feel the stability of the cosmos, where mass and energy govern time and space with precise rules, ensuring predictability and coherence across scales. Even in extreme astrophysical events, the behavior of energy and mass remains consistent with observational evidence. Colliding galaxies provide additional insight. As galaxies interact, kinetic energy and gravitational potential energy reshape their paths and the surrounding spacetime. Stars, gas, and dark matter redistribute according to the combined influence of mass and motion. You follow these processes in imagination, noting the measured consequences for time and space. Observations across millions of light-years reinforce the principle that energy and mass, in all their forms, continuously influence the geometry of the universe. You reflect on how energy converts into mass in high-energy processes. In the early universe, photons of sufficient energy produced particle-antiparticle pairs, demonstrating the dynamic interchange of energy and mass. This interplay shaped the evolution of the cosmos, influencing both large-scale structure and the passage of time at microscopic and macroscopic levels. You sense the continuity of these processes, tracing the consistent principles that govern all energy-mass interactions. Nuclear reactions in stars, particle collisions, and black hole mergers all reveal the universality of E = mc². Time dilation near massive objects, gravitational lensing, and cosmic expansion all respond predictably to the mass-energy content. You appreciate the calm, exact relationship. Energy influences spacetime, mass curves time, and the universe obeys these rules at every scale. Each observation reinforces the consistency of nature and the precise flow of temporal intervals in response to energetic and massive phenomena. As your awareness settles, you notice that energy and mass are inseparable in shaping the cosmos. Every particle, star, and galaxy carries both mass and energy, contributing to the curvature of spacetime and the pacing of time itself. Observations from particle accelerators to distant supernovae confirm the predictable influence of these quantities. You sense the quiet coherence of the universe, where energy, mass, and motion continuously modulate the flow of time, preparing your mind to explore the more theoretical possibilities that emerge when these principles are extended to hypothetical structures like time machines. You allow your attention to rest on the theoretical boundaries of spacetime, exploring configurations that suggest the possibility of returning to earlier moments or traveling forward along different temporal paths. General relativity provides equations that, under extreme conditions, permit unusual geometries in spacetime. These solutions do not imply that time travel is simple or feasible with current technology, but they do demonstrate that the universe, governed by precise physical laws, allows for unusual temporal structures under specific constraints. One example is the Tipler cylinder, a hypothetical object of infinite length that rotates at immense speeds. Its rotation would drag spacetime around it, producing a phenomenon called frame dragging. You picture the cylinder spinning, gradually twisting the surrounding geometry. Mathematical solutions indicate that a sufficiently long and dense cylinder could create closed time-like curves, paths that, in theory, loop back in time. You notice the careful precision required. Even small deviations in mass, length, or speed alter the geometry and the resulting paths. Traversable wormholes provide another example of theoretical time travel. Unlike unstable Einstein-Rosen bridges, a wormhole stabilized with exotic matter could connect distant regions of spacetime. If one mouth of the wormhole experienced time differently from the other, perhaps by moving at relativistic speeds or being placed near a strong gravitational field, then an object entering one end could emerge at an earlier moment relative to distant observers. You sense the mathematical clarity behind this concept, grounded in the curvature of spacetime rather than conjecture. Energy requirements impose stringent limits. Exotic matter with negative energy density is necessary to maintain the stability of traversable wormholes. You consider that negative energy has been observed in small amounts in quantum phenomena, such as the Casimir effect, but nowhere near the scale required to sustain a macroscopic tunnel. The universe allows these solutions in principle, yet practical realization remains extraordinarily constrained. You focus on the precision of the calculations, noting how small differences in energy distribution drastically alter spacetime geometry. Causality presents another boundary. Closed time-like curves imply that events could influence their own past, raising potential paradoxes. You reflect on this gently, understanding that the laws of physics provide mechanisms to limit these scenarios. Hawking's chronology protection conjecture suggests that quantum effects may prevent macroscopic violations of causality, effectively preserving the sequence of cause and effect. You sense that even in extreme geometries, the universe enforces logical consistency, maintaining a coherent temporal order. Rotating black holes or Kerr black holes provide insight into theoretical time travel. Their inner regions contain solutions resembling closed time-like curves. You imagine a trajectory that threads carefully through this region, observing how spacetime loops back. Practical passage is impossible, not only because of the extreme gravitational forces but also because of stability and energy constraints. The mathematics, however, illustrates that general relativity permits temporally unusual geometries, confirming the flexibility and precision of the equations. Tipler cylinders, wormholes, and Kerr black holes all illustrate that time is responsive to extreme spacetime curvature. You visualize the precise paths of hypothetical travelers, noting how small changes in geometry or motion affect the outcome. Each calculation follows strict rules. The universe does not allow arbitrary manipulation, only configurations consistent with energy, momentum, and the curvature dictated by Einstein's equations. You feel the quiet order of these possibilities, even if they remain inaccessible in practice. Quantum effects introduce additional limits. Vacuum fluctuations, particle creation, and energy constraints interact with extreme geometries. A traversable wormhole, even if theoretically possible, may be destabilized by quantum back reaction. You imagine spacetime gently resisting such distortions, maintaining coherence in spite of high-energy perturbations. Observations and calculations show that the universe enforces balance, ensuring that extreme geometries do not produce uncontrolled or unphysical outcomes. Mathematical consistency guides every consideration. Tipler cylinders must be infinitely long in classical solutions, wormholes require exotic matter in precise amounts, and Kerr black hole paths demand careful positioning. You perceive the universe as a system governed by exact equations, where time can bend and loop only under specific conditions. Each scenario reinforces that the flexibility of spacetime is constrained by energy, mass, and motion, and that calculations predict these effects with exacting precision. You reflect on the interplay between theory and observation. While no practical time machines exist, astrophysical observations provide benchmarks. The behavior of neutron stars, black holes, and gravitational waves confirms the predictions of general relativity under extreme conditions. These measurements ensure that theoretical time travel proposals are evaluated against the actual behavior of spacetime. You sense the reassuring alignment of mathematics and observation, reinforcing that unusual geometries are explored within a rigorous, factual framework. Traveling along a closed time-like curve requires precise synchronization. Any deviation in velocity, mass, or energy distribution alters the path, potentially rendering it non-closed or unstable. You imagine a journey in which the traveler must follow exact instructions to navigate the curvature correctly. The precision required underscores the challenge. The universe permits the mathematical solution, but practical application demands conditions far beyond what current technology can achieve. You notice the subtle guidance of natural limits. Time machines in theory also highlight the universality of physical laws. Energy and mass dictate the curvature of spacetime, which in turn governs temporal intervals. The equations are consistent across all scales, from subatomic particles to supermassive black holes. You sense that these extreme configurations, though hypothetical, reveal the full flexibility of spacetime while respecting the same underlying principles observed throughout the universe. Each prediction is grounded in measurable physics. Causality constraints and energy requirements combine to enforce natural boundaries. You consider that even if a hypothetical structure allowed backward temporal travel, quantum effects and gravitational instabilities would likely prevent macroscopic violations. The universe maintains order, balancing the possibility of unusual geometries with the consistency of cause and effect. You sense the delicate equilibrium that preserves the integrity of time across all scales. You reflect on how relativistic motion affects time. If one mouth of a wormhole travels at near-light speeds relative to the other, time dilation creates a difference in the passage of time between the two ends. This principle, already verified by atomic clocks and satellite systems, underpins the theoretical time travel mechanism. You appreciate the seamless connection between verified relativistic effects and the predictions of extreme geometries, reinforcing the coherence of physical law. Even in the most speculative solutions, the universe behaves predictably. Closed time-like curves, traversable wormholes, and Tipler cylinders all obey the same fundamental rules of relativity, energy, and causality. You sense the quiet order, recognizing that time's flexibility is bounded by measurable laws. The theoretical exercises illuminate the limits and possibilities of spacetime, demonstrating both the elegance of the equations and the precision with which nature enforces them. Your awareness rests in the balance between possibility and constraint. Time can bend, loop, and stretch under extreme conditions, but the universe requires exacting parameters to maintain stability and consistency. Observational evidence, from black holes to high-energy astrophysical phenomena, confirms the reliability of these principles. You feel the calm coherence of a universe that allows intricate structures while safeguarding the logical flow of cause and effect. As you consider these possibilities, you notice that spacetime, even in its most extreme forms, follows predictable patterns. Energy, mass, and motion collectively determine the curvature that shapes temporal pathways. Hypothetical time machines illustrate the boundaries imposed by nature, revealing both the flexibility and the limits of temporal flow. You sense the quiet invitation to explore these boundaries further, reflecting on how time behaves across scales and preparing to observe its interaction with quantum phenomena in the microscopic realm. You let your mind shrink to the microscopic scale, where the familiar rules of everyday physics give way to quantum principles. At this level, particles do not have definite positions or velocities until they are measured. Instead, they exist in superpositions, simultaneously occupying multiple states. You imagine observing electrons and photons in this delicate state, their behavior described by wave functions that evolve according to precise mathematical laws. Time still progresses, but its relationship to these states is subtler than in the macroscopic world. Entanglement illustrates a remarkable connection between distant particles. When two particles become entangled, the measurement of one instantaneously influences the state of the other, regardless of separation. You picture two photons generated in a lab, moving apart in opposite directions. Measuring the polarization of one immediately determines the polarization of the other. Experiments have confirmed this effect repeatedly, demonstrating that quantum correlations exist across space, while still respecting the constraints of relativity. Time, in this context, is encoded in the sequence of measurements and the evolution of the wave function. You focus on how quantum superposition interacts with time. Consider a particle in two possible energy states. Until measured, it does not choose one path over the other. Instead, it evolves according to the Schrödinger equation. The probabilities of observing each state change with time in a predictable manner. You sense the slow, rhythmic unfolding of quantum evolution, guided by well-established mathematics. Even though the particle's state is indeterminate, its temporal evolution is precise, providing a bridge between uncertainty and predictability. Experiments such as delayed choice and quantum eraser tests illustrate how temporal correlations manifest. In these setups, the outcome of a measurement seems to depend on choices made after a particle has passed through an apparatus. You reflect on the careful design and rigorous interpretation of these experiments. While they might seem paradoxical, they do not violate causality. They reveal the subtleties of quantum information and its relationship to time. Observers see correlations that are consistent with quantum mechanics, reinforcing the theory's predictive accuracy. You consider the role of energy and frequency in temporal evolution. The phase of a quantum state oscillates over time according to its energy. You imagine a photon with a specific energy, its wave function evolving smoothly, producing interference patterns that reveal precise timing information. Even in a world of probabilistic outcomes, time remains a reliable parameter in the evolution of quantum systems. Each oscillation, each interference fringe, encodes the passage of time at the microscopic level. Quantum clocks, devices that measure time using transitions between energy levels, provide another window into temporal behavior. These clocks achieve extraordinary precision, sensitive to effects such as relativistic time dilation. You picture ions or atoms trapped and observed as they oscillate between states, producing regular ticks. Their evolution follows quantum mechanics, yet the ticking is measurable and predictable. These clocks connect quantum phenomena with macroscopic timekeeping, linking the two domains through precise experimental observation. You reflect on decoherence, the process by which quantum systems interact with their environment. Superpositions gradually collapse into definite states due to these interactions. Time plays a critical role here. The rate of decoherence depends on environmental conditions and energy exchanges. You sense that the microscopic world, though governed by probability, evolves consistently, with time providing a framework for these transitions. The universe preserves the predictability of outcomes even as individual states remain indeterminate until observed. Quantum entanglement also raises questions about temporal order. Measurements separated in time can exhibit correlations that classical intuition would not predict. You consider experiments verifying that the sequence of measurements aligns with the statistical predictions of quantum theory. The results are repeatable, reliable, and consistent with the rules of quantum mechanics. Even when events appear counterintuitive, temporal consistency is maintained in the probabilities and correlations, demonstrating the subtle but precise interplay between quantum states and time. You explore the energy-time uncertainty principle. Similar to the position-momentum uncertainty, it states that the product of uncertainty in energy and uncertainty in time has a lower bound. You imagine a particle observed over a brief interval. The shorter the measurement, the less precisely its energy is determined. This principle does not make time itself uncertain. Rather, it quantifies limits on simultaneous knowledge of energy and temporal duration. You feel the subtle constraints imposed by quantum mechanics, illustrating the structured nature of time at microscopic scales. Experiments with quantum teleportation reveal how information, constrained by quantum laws, propagates across spacetime. Entangled states are used to transfer quantum information from one location to another without moving matter itself. You sense that temporal consistency is maintained, as classical communication is still required to complete the process. The universe enforces causality, even while allowing instantaneous correlations between entangled particles. Time, in this sense, provides the scaffolding within which quantum events unfold. You observe that quantum fluctuations contribute to the energy content of empty space. Even a vacuum is not truly empty. It exhibits temporary energy variations that obey the rules of quantum field theory. These fluctuations influence phenomena such as the Casimir effect and virtual particle creation. You sense the subtle temporal rhythm of these processes, where the universe maintains strict consistency at all scales, blending microscopic indeterminacy with predictable statistical behavior over time. Quantum mechanics also informs cosmology. The early universe's evolution depends on quantum fluctuations that seeded the formation of galaxies and large-scale structures. You imagine these tiny variations, amplified by cosmic expansion, shaping the universe we observe today. The microscopic interplay of energy and time thus has macroscopic consequences, demonstrating that quantum processes are woven into the larger temporal fabric of the cosmos. Observations of the cosmic microwave background confirm these predictions, providing evidence of quantum influence across billions of years. You reflect on how classical and quantum notions of time interact. Classical physics treats time as continuous and uniform, while quantum theory emphasizes probabilistic evolution and correlations. Yet experiments show that both frameworks are compatible. Quantum systems evolve in time, and macroscopic clocks measure intervals reliably. You feel the harmony between the domains, understanding that time in the universe is continuous, measurable, and consistent, even as individual particles exhibit inherent uncertainty in their states. Finally, you notice that quantum mechanics challenges intuition but not factual consistency. Time remains a parameter that structures evolution, correlations, and energy exchanges. Observations confirm superposition, entanglement, and decoherence, all unfolding within a temporal framework that is coherent and predictable. You sense the quiet precision with which the universe integrates quantum behavior into the continuous flow of time, offering both subtlety and clarity in the evolution of matter and energy at the smallest scales. As your mind rests in this awareness, you perceive that the microscopic world enriches your understanding of time. Quantum correlations, superpositions, and temporal probabilities reveal the universe's subtle rhythms, complementing classical observations and relativistic effects. You feel the intricate interplay between energy, mass, motion, and measurement, sensing that even at the smallest scales, the flow of time is structured, reliable, and intimately connected to the fundamental properties of matter and energy across space. You begin by tracing the journey of light across the universe. Every photon that reaches you has traveled for millions or billions of years, carrying information about the moment and place where it was emitted. Observing a distant galaxy is therefore like looking backward in time. The light you receive preserves the history of cosmic events, allowing astronomers to measure the age and evolution of structures far beyond your local environment. Each photon is a messenger, precise and consistent, guiding your understanding of time across vast distances. Standard candles provide a reliable method for measuring cosmic distances and time intervals. Type Ia supernovae, for example, explode with a predictable intrinsic brightness. You imagine astronomers comparing observed brightness with expected values, determining how far away the explosion occurred. The time taken by light to reach Earth reflects the duration since the supernova occurred. By measuring many such events across different distances, scientists construct a timeline of the universe's expansion, embedding temporal information in each observation. Pulsars offer another precise measure of time. These rapidly rotating neutron stars emit pulses of radio waves at consistent intervals, sometimes hundreds of times per second. You visualize a pulsar spinning steadily, each pulse arriving like a metronome from across space. Variations in the timing of pulses reveal gravitational influences, orbital motion, or interstellar medium effects. The stability of pulsars allows astronomers to track time with extraordinary precision, effectively providing clocks that span the galaxy and extend your awareness of temporal flow far beyond your immediate environment. Redshift remains a critical tool for understanding cosmic time. As space expands, the wavelength of light stretches, shifting toward the red end of the spectrum. By measuring redshift, astronomers determine both the distance of the source and the epoch from which the light was emitted. You sense the subtle relationship between observed wavelength and cosmic history, noting that higher redshift corresponds to earlier times. This provides a chronological map, revealing how galaxies and clusters evolved over billions of years. Gravitational waves introduce a new dimension in observing time. These ripples in spacetime, produced by events such as colliding black holes or neutron stars, travel at the speed of light, carrying precise information about the dynamics of massive systems. You imagine detectors like LIGO and Virgo measuring distortions smaller than a proton, registering the passage of waves that originated millions of light-years away. Each signal encodes both the spatial and temporal structure of the event, allowing you to track time across extraordinary scales. You reflect on the combination of multiple observational methods. By integrating light, pulsar timing, and gravitational waves, astronomers construct a coherent temporal framework for the universe. Each measurement cross-validates others, ensuring accuracy. You sense the precision of these techniques, independent observations converging to provide consistent information about the evolution of stars, galaxies, and cosmic structures over billions of years. Time emerges as both measurable and structured, extending naturally from local to cosmic scales. You consider how light from distant supernovae appears to unfold more slowly than nearby events, a consequence of cosmic expansion. This temporal stretching, combined with redshift, provides a direct measure of how spacetime evolves. Observers can reconstruct the true duration of explosions by accounting for expansion effects. You feel the gentle reliability of these measurements, noting that even the most distant phenomena conform to predictable rules. The universe provides both signals and the tools to interpret them accurately. Large-scale surveys map cosmic structures across vast distances. Galaxy clusters, voids, and filaments all encode temporal information. You visualize astronomers measuring positions, redshifts, and velocities, constructing three-dimensional maps that reveal how matter has moved and evolved over time. The patterns in these distributions reflect both gravitational dynamics and the expansion of space. Your mind absorbs the quiet regularity of these structures, appreciating how observations can extend your awareness of time across billions of years. You reflect on the light from the earliest galaxies, formed less than a billion years after the Big Bang. Observing this ancient light requires extreme precision, correcting for redshift, lensing, and absorption by interstellar matter. You imagine photons traveling for over 13 billion years, their journey a precise record of the early universe. Observing these galaxies allows scientists to infer how matter coalesced, how stars ignited, and how cosmic time unfolded in the first epochs of existence. Each measurement deepens your sense of temporal continuity across cosmic scales. Gravitational lensing offers another way to probe time. Massive objects bend the path of light, producing multiple images of the same source. By measuring the delays between light paths, astronomers can infer distances and the curvature of spacetime. You sense the precision of these observations. Tiny temporal offsets encode the geometry and distribution of matter across vast regions. Time, in this context, is both a parameter to measure and a consequence of spacetime's curvature, revealing the intimate connection between temporal flow and cosmic structure. You consider cosmic chronometers, such as the decay of radioactive elements in stars and galaxies. Observing ratios of isotopes provides independent estimates of age. These methods complement redshift and pulsar timing, providing additional verification of the temporal history of the universe. You imagine examining a distant galaxy, tracing the decay of elements over billions of years, each ratio a fingerprint of elapsed time. The convergence of multiple methods reinforces the reliability of cosmic temporal measurements. You reflect on the interaction between light and gravitational waves. Both propagate across spacetime, carrying information about when and where events occurred. By comparing these signals, astronomers reconstruct the timing and sequence of distant phenomena. You sense the remarkable precision with which time can be inferred from the cosmos, noting that even billions of light-years away, the universe preserves a coherent record of events. Each observation strengthens the connection between what is observed and the passage of time across space. You notice the interplay between local measurements and cosmic scales. Atomic clocks aboard satellites, pulsars, and distant supernovae all operate within the same framework of temporal consistency. Observations of the universe confirm that local timekeeping aligns with cosmic time. You feel the unity of temporal measurement, from microscopic processes to events spanning billions of years. Time emerges as a structured, continuous flow that links the smallest particles to the largest cosmic structures. Finally, you consider the future of observing time. Improved detectors, more sensitive telescopes, and advanced gravitational wave observatories will extend the reach of temporal measurement. You imagine following events ever more precisely, refining estimates of cosmic expansion, stellar evolution, and gravitational dynamics. Each improvement allows you to track the universe's history with increasing clarity. Time, measured and observed, becomes a continuous thread linking photons, waves, and matter across the cosmos. As your awareness settles, you perceive that the universe maintains a coherent temporal record. Photons and gravitational waves convey reliable information about past events, while local and distant measurements align in predictable ways. Observations of supernovae, pulsars, and early galaxies reveal billions of years of cosmic history. You feel the quiet reassurance that the flow of time across the universe is measurable, structured, and deeply interconnected, gently preparing your mind to explore the limits and constraints that govern this temporal order. You begin by focusing on the rules that govern cause and effect. The universe enforces a logical sequence. Actions lead to consequences, and these relationships are embedded in the structure of spacetime. While mathematical solutions to Einstein's equations suggest the possibility of unusual geometries, such as closed time-like curves, the physical requirements to implement them are extreme. You sense the quiet precision of these rules, understanding that nature imposes limits to preserve consistency and prevent contradictions. Causality is the first constraint. If an event could influence its own past, paradoxes would arise. You imagine attempting to alter an event that has already occurred. Even in a hypothetical universe where spacetime can loop, mechanisms appear to prevent logical contradictions. Hawking's chronology protection conjecture proposes that quantum effects intervene to maintain causal order, preventing macroscopic violations. You feel the reassurance that the universe safeguards the integrity of time, even where extreme curvature exists. Energy requirements present another boundary. Tipler cylinders, traversable wormholes, and other theoretical time machines require immense energy densities, often far beyond what is physically available. You imagine stabilizing a wormhole. The negative energy needed exceeds what can be produced with current or foreseeable technology. Even if energy could be concentrated, precise distributions are essential. Nature does not allow arbitrary manipulation. Every configuration must obey strict conservation laws. Time's flexibility is bounded by what is physically achievable. Quantum effects impose further limits. Fluctuations in vacuum energy, particle creation, and backreaction of quantum fields can destabilize extreme geometries. You picture spacetime gently resisting distortions that violate energy or causality constraints. Observations confirm that quantum effects enforce subtle corrections, ensuring that macroscopic violations of time's flow do not occur. Even in thought experiments, these quantum safeguards preserve the structure of reality, maintaining consistent temporal order. Black holes illustrate practical limitations. While solutions within Kerr black holes permit closed time-like curves mathematically, the environment is hostile. Tidal forces near the singularity would destroy matter long before a traveler could navigate the required path. The equations are precise, but physical survival is impossible. You sense the distinction between theoretical possibility and practical feasibility. The universe allows certain solutions, yet imposes conditions that prevent their realization in a physical context. Speed and relativity also define constraints. Time dilation allows travelers at near-light speeds to experience slower time relative to distant observers, a principle confirmed by atomic clocks in spacecraft and satellites. However, reaching such speeds requires enormous energy and precise navigation. You imagine accelerating a spacecraft to fractions of light speed, noting that relativistic effects become significant only under extreme conditions. The universe demonstrates time manipulation through relativity, but only in ways that are measurable, limited, and constrained by energy. You reflect on gravitational limits. Spacetime curvature can bend light and slow time near massive objects. Yet producing curvature sufficient for macroscopic backward time travel requires mass energy far exceeding known sources. You visualize attempting to replicate this effect artificially, realizing that even small deviations in mass or energy distribution prevent the desired temporal loop. The universe enforces order, mass energy determines curvature, and only configurations consistent with physics are allowed. Paradoxes remain a subtle consideration. Concepts like the grandfather paradox illustrate the logical challenges of altering past events. If changes to history were possible, contradictions could arise, yet nature maintains consistency. You sense that even extreme geometries, if realized, are constrained by rules that preserve causal sequences. These limits are not arbitrary. They emerge from the interplay of relativity, quantum mechanics, and energy constraints, demonstrating that time structure is robust and consistent across scales. The scale of space also imposes limits. Time travel scenarios often require regions of spacetime that are extraordinarily large or precisely shaped. Tipler cylinders must be infinitely long, and stable wormholes require exact geometries. You notice that the universe provides natural boundaries. No infinite cylinders exist, and exotic matter for wormholes is scarce. Even within these hypothetical frameworks, practical realization is prevented by the finite, measurable nature of the cosmos. You consider observational evidence for these limits. No astrophysical phenomenon indicates that macroscopic backward time travel occurs. Measurements of pulsars, supernovae, and gravitational waves consistently align with expected causal sequences. You feel the reassurance of this observational consistency. The universe behaves predictably, with time flowing in a manner that matches both classical and quantum expectations. Extreme geometries exist as mathematical possibilities but are constrained by measurable reality. You reflect on the combination of factors that prevent time travel. Causality, energy limits, quantum effects, survival constraints, and spatial requirements all interact to maintain temporal integrity. You notice how these constraints reinforce one another. Violating one condition often violates others, creating a system of checks that preserves consistency. Time's apparent flexibility in equations is tempered by the reality of physical, measurable limits, ensuring that the flow of events remains coherent. Relativistic effects provide a subtle form of temporal manipulation, but they do not allow paradoxical changes to history. Satellites in orbit experience measurable time dilation relative to Earth, confirming Einstein's predictions. You imagine atomic clocks ticking at slightly different rates, demonstrating that time is relative, yet still consistent with the laws of physics. These effects are observable, precise, and predictable, illustrating that while time can be stretched or slowed, it cannot be arbitrarily reversed. You also consider cosmological boundaries. Cosmic expansion defines horizons beyond which light and information cannot reach an observer. You sense that even at the largest scales, nature imposes limits on the transmission of events and information. Spacetime has structure, and its expansion and geometry create natural constraints on what can be observed and influenced. Time travel to distant points or epochs is therefore further restricted by the vast distances and velocities involved. Even thought experiments highlight natural limitations. Hypothetical constructs such as wormholes or rotating cylinders provide valuable insights into spacetime, yet practical realization remains prohibited by measurable physics. You observe the careful balance between mathematical possibility and physical feasibility. The universe allows precise exploration of these extremes, but always within bounds defined by energy, mass, quantum behavior, and causality. Your attention rests on the consistency of these limits. Time can be influenced, slowed, or dilated under extreme conditions, yet the sequence of events remains orderly. Observations confirm that the universe maintains temporal integrity across scales, from atomic transitions to galactic motions. You feel the quiet reassurance that nature enforces continuity, even where equations suggest exotic possibilities. Time structure is both flexible in theory and bounded in practice. Finally, You notice that understanding these limits strengthens your appreciation for the universe's coherence. Spacetime bends in response to energy and mass, relativity governs motion, and quantum mechanics constrains microscopic behavior. Together, these principles prevent paradoxes, enforce causality, and define the measurable boundaries of temporal manipulation. You sense the calm order of a universe where time flows predictably, even as its equations allow theoretical exploration of extraordinary geometries. As your mind rests in this awareness, you perceive that time is structured, flexible only within strict physical limits, and governed by a combination of relativity, energy constraints, and quantum principles. You sense the balance between possibility and restriction, the harmony between equations and observation. This precise framework prepares your awareness to consolidate all these insights, reflecting on the flow of time from the smallest scales to the largest, and the cumulative understanding of spacetime you have gained throughout this journey. You begin by letting your mind revisit the path you have traced through the universe of time. From the quiet bending of spacetime around massive bodies to the intricate evolution of quantum states, each step reinforces the structure and coherence of temporal flow. You feel the subtle stretching of moments near stars and black holes, observing how gravity slows time, confirmed by decades of precise measurement. Atomic clocks on satellites tick more quickly than those on Earth's surface, illustrating that even small differences in gravitational potential produce measurable temporal shifts. You reflect on the way mass and energy shape the curvature of spacetime. Neutron stars and black holes, dense beyond imagination, create local distortions that influence the passage of time. Light and matter trace these curves, traveling along paths determined by geometry. Gravitational lensing, observed in distant galaxies, confirms that these distortions are real, bending the paths of photons and providing a record of the curvature. You sense the quiet order of the universe, where energy and mass govern the rhythm of time itself. Cosmic expansion now returns to your awareness. The stretching of space, measured through redshift, carries temporal information across billions of light-years. Light from distant galaxies reflects an earlier universe, preserving the sequence of cosmic evolution. Standard candles like supernovae provide reliable markers, and pulsars act as precise cosmic clocks. You feel the gentle continuity of time across immense distances, aware that the universe maintains a structured history accessible to careful observation and measurement. Quantum processes enrich this picture. Superposition, entanglement, and temporal correlations illustrate that at microscopic scales, time interacts with probability and information. You recall experiments where the sequence of measurements reveals subtle dependencies and where quantum fluctuations influence the early universe. Decoherence ensures that these microscopic states ultimately resolve into macroscopic reality, maintaining consistency with classical time while revealing a deeper layer of temporal structure. You sense the harmony between quantum uncertainty and observable order. Time travel proposals now settle into perspective. Tipler cylinders, traversable wormholes, and Kerr black holes illustrate that the equations of general relativity permit unusual geometries. Yet practical constraints, energy requirements, causality, quantum effects, and stability make such journeys unreachable. You observe the universe as both flexible and disciplined, allowing theoretical exploration of time while enforcing strict boundaries. Causality persists, ensuring that events unfold logically, even where spacetime curves in extreme ways. You reflect on the interplay between relativistic and quantum effects. High velocities slow time, strong gravity influences clock rates, and quantum states evolve in probabilistic yet measurable ways. Observational evidence confirms these principles at every scale, from GPS satellites to gravitational wave detections. You feel the quiet precision of this system, recognizing that time's flow is both consistent and responsive to the conditions of space, mass, and energy. The universe provides a reliable framework within which all processes unfold. Observational techniques reinforce your understanding. Photons from distant stars, gravitational waves from colliding black holes, and the timing of pulsars provide convergent information about the temporal structure of the cosmos. Each observation, precise and repeatable, confirms that time can be measured, compared, and understood across vast scales. The universe maintains a continuous temporal record, allowing you to trace the evolution of matter, energy, and space with clarity and confidence. You consider the limits observed in practice. While equations suggest extraordinary possibilities, the physical universe imposes boundaries. Energy densities, quantum back reaction, and gravitational constraints prevent paradoxical time loops or macroscopic violations of causality. Even extreme environments, like the interior of a rotating black hole, remain inaccessible in practice, reinforcing that nature balances flexibility with order. You sense the quiet strength of these limits, preserving the coherence of temporal flow across the cosmos. The cumulative view now emerges. From the smallest quantum fluctuations to the largest cosmic structures, time is both a measurable parameter and a dynamic component of the universe. Gravity, mass, energy, and motion interact to determine the precise rate at which time passes in any location. You feel a deep calm in the reliability of these interactions. The universe unfolds predictably, and each phenomenon contributes to a coherent temporal framework. You sense continuity across scales, where microscopic and macroscopic time coexist seamlessly. You reflect on your own perception of time in this vast framework. Local clocks, daily routines, and human experience unfold within the larger cosmic flow. Yet, you are aware that spacetime is flexible, responsive to energy, and shaped by geometry. Relativistic and quantum effects remind you that time is not uniform everywhere, but your understanding allows you to contextualize these differences. You feel a quiet appreciation for the precision with which the universe maintains both local and cosmic temporal order. You consider the history preserved in light. Each photon, each gravitational wave, carries a record of the past. By observing these signals, scientists reconstruct sequences of events with extraordinary accuracy. Supernovae, galactic evolution, and the cosmic microwave background all encode information about temporal progression. You sense the gentle reliability of these signals, as if the universe itself provides a ledger of its history, allowing time to be traced and understood across billions of years. Cosmic expansion and quantum fluctuations intertwine in your awareness. The growth of structure, from galaxies to clusters, emerged from microscopic processes that unfolded within the expanding universe. Observations of the cosmic microwave background confirm these patterns, showing that the smallest quantum variations influenced large-scale temporal development. You feel the quiet intricacy of this system, where time is both local and global, microscopic and cosmic, measurable and predictable. Energy and mass continue to guide temporal behavior. Rotating neutron stars, orbiting black holes, and colliding galaxies all demonstrate that time's passage is sensitive to local conditions. Atomic clocks, pulsar timing, and gravitational wave measurements confirm predictions with remarkable precision. You perceive the universe as a system of interconnected processes, each obeying consistent laws, each contributing to a coherent flow of events. Time is both dynamic and disciplined, offering structure to all phenomena. As your awareness settles, you reflect on the balance between possibility and limitation. General relativity allows time to bend, quantum mechanics permits subtle correlations, and cosmic expansion stretches intervals across billions of years. Yet the universe enforces constraints that maintain consistency, causality, and stability. You feel the quiet wisdom of these natural limits, knowing that even where equations suggest unusual scenarios, reality preserves the coherent progression of events. Time is structured, reliable, and measurable. Finally, you sense a calm curiosity lingering in the mind. The universe presents a temporal landscape that is rich, intricate, and precise. Observations, theory, and measurement all converge to reveal how space-time behaves, how energy and mass influence the flow of moments, and how quantum effects add subtlety to the macroscopic order. You feel connected to a cosmos where time is a tangible, measurable, and beautifully consistent aspect of reality, inviting gentle exploration, reflection, and rest. Your mind rests in this awareness, embracing the quiet continuity of time from the smallest particles to the largest galaxies. The universe has revealed its laws with clarity and precision, and your understanding now extends across scales, from relativistic effects to quantum interactions and cosmic expansion. In this calm observation, you sense the rhythm of time itself, steady, coherent, and ever-present, guiding the unfolding of events and offering a deep, factual reassurance as your awareness drifts peacefully into rest.